In the present lecture, we will discuss the stress-strain diagram for ductile material. In general, mechanical properties of material are determined by performing the tensile test on a cylindrical specimen of the material. Loads are measured on the main dial of the machine and the elongations are measured with the help of the extensometers. Then we have to plot the stress on vertical axis and strain on horizontal axis to determine the mechanical properties of material. So here figure shows the stress strain diagram for a typical structural steel specimen under the tensile loading. Here strains are plotted on the horizontal axis and stresses are plotted on the vertical axis. So next we will discuss the various points on the stress strain curve. So first point is the point A, that is the proportionality limit. So here observe, from point O to point A the curve is straight and linear, and hence proportionality limit is the limiting value of stress up to which stress is directly proportional to strain, and hence Hooke's law holds valid up to this point A. So in the previous lecture we discussed the Hooke's law and it is stated that stress is directly proportional to the strain up to the proportionality limit. So here point A is the proportionality limit and Hooke's law is valid up to this proportionality limit. And here observe that one so curve is a straight and linearly it is varying. So it is the straight line curve. It is indicating that one stress is directly proportional to the strain. So this point A we are calling as the proportionality limit and Hooke's law is valid up to this point A. So next we have to see the next point on the stress strain curve, that is the point B. So point B is the elastic limit. The point B is slightly behind point A and it is known as the elastic limit. Up to the point B, the material will regain its original size and shape when load is removed. This indicates that the material has elastic properties up to the point B. So in the previous lecture already we discussed elastic material mean the material regain its original size and shape when the load is removed. So here also the point B is the elastic limit. So we are applying the load up to the point B. So the material possesses the elasticity property. So after crossing the load point B, the material will be lose the elasticity property. So the point B on the curve we are calling as the elastic limit. So after the point B, it will goes to the permanently plastic stage. Behind this point B is the material possesses the elasticity property. Next we will discuss the next point on the stress strain curve, that is the point C. Point C is the upper yield point. So first we will look for the what you mean by yielding, then we will discuss the upper yield point, point C, and lower yield point D. If the material is stressed behind the point B, plastic deformation starts and the material does not regain its original size and shape upon unload, and this phenomena is called as the yielding. So if the material continuously stressed behind the point B, so then material enters into the plastic deformation. So this phenomena we are calling as the yielding. So next we look for the what you mean by upper yield point. So upper yield point is a point at which maximum load or stress required to initiate the plastic deformation or yielding of the material is called as the upper yield point, that is point C. So at this point the dislocations or slip in the crystal structure starts to moving. So upper yield point indicates the start of plastic deformation with resistance. So next we look for the next point, that is the lower yield point. So that is the point D. As the dislocations or slip is taking place in the material, it offers less resistance to the material and hence the curve falls slightly. So here observe, so point C and point D, curve is slightly falls from the point C to point D. Reason is at the point C dislocations or slip initiated. So at the initial stage we require the very high resistance and require the very high load. But at the point D already dislocations are initiated, then it will be just continuously that dislocations. So that's why here less amount of the forces are required to these dislocations. So next we have to see for the what you mean by lower yield point. A point at which minimum load or stress required to maintain the plastic deformation or yielding of the material is called as the lower yield point. So dislocation or slip become too much in number and it will be restrict the each other movement. So that is the reason, so why the material does not regain its original shape and sizes after the removal of the load mean. So here, so dislocation and slip is generated, so it's a come back to its original state is very difficult. Okay, next to have, so lower yield point indicates the continuation of plastic deformation with less resistance. Okay, next we have to look for the next point on the stress strain curve is the point E, that is the ultimate stress point. So after the lower yield point, point D, strain hardening in the material takes place. First we have to look for the what you mean by strain hardening. Strain hardening, also we are calling as the work hardening, is the process where a ductile material becomes stronger and harder as it is plastically deformed. So strain hardening, also known as work hardening, is the strengthening of material occurs because of dislocation movements within a crystal structure of the material, and hence there is a positive rise in the curve from D to E. So have to observe from D to E, so material strength is increasing. So due to this dislocation strengthening properties. And one more thing I have to observe, in this region stress increases, strain also increases at point E, and the specimen takes the maximum load and the corresponding stress at the point E we are calling as the ultimate stress point. So here observe from the stress strain diagram. So maximum stress is occur taking the specimen maximum load at the point E only. So this point E we are calling as the ultimate stress point. So ultimate stress means the capability of the material which has to be withstand at highest load. Okay, next we will look for the next point on the stress strain curve, that is the point F, that is breaking point. Behind the ultimate stress point is reached, necking takes place and the cross-sectional area considerably decreases. Then load carrying capability of the specimen reduces, and hence in the portion E to F, strain is increases with decreases in stress. So behind the ultimate stress point and continuously we are stressing the specimen, then its cross-sectional area it will be reduces. That is we are calling as the necking. Then load carrying capability of the specimen it will be reduced. So obviously it will be strength will be reduces. So stress value it is decreasing, but strain value is increased. So large deformation is possible at the low level of the load. So that's why. So after reaching the ultimate point, stress is decreasing and strain value is increases. And at the point F, specimen breaks. The stress at the point, at this point breaking point, we are calling as the breaking stress or fracture stress. So next we have to discuss the ductility of a material in a tension can be characterized by its elongation and by the reduction in area at the cross section where the fraction occur. So ductility of the material we can be characterized by the two conditions. First one is the percentage of elongation. Second one is the percentage of reduction in the cross sectional area. So percentage of elongation is the ratio of the extension in length of the specimen after fracture to its initial gauge length. Generally this is expressed in the terms of percentage. So percentage of elongation equal to the final length minus initial length divided by initial length into the 100. So next we have to look for the percentage reduction in area. So percentage of reduction in area equal to initial area minus final area divided by initial area into the 100. So next we have to look for the true stress strain and the engineering stress strain. So let P is be the load and A0 is the original cross section area and A is the area of cross section at any instant. So A0 is the initial original cross sectional area and A is the respected instant cross sectional area of the specimen, and let consider the P is the applied load. Then engineering stress is defined as the applied load divided by the original cross section area of the material, also known as the normal stress. Then engineering stress equal to the load divided by original cross section area of the specimen, that is the P divided by A0. Then we have to look for the true stress. True stress is the applied load divided by the actual cross sectional area of the specimen at that load. So actual cross section area means it will be changing in area with respect to the time. At respected instant we will get the different cross sectional areas. Then true stress equal to the load divided by actual area of cross section at any instant, that is the P divided by capital A. Similarly, I have to look for the engineering strain. So engineering strain is the change in length to original length in a tensile test, also known as the normal strain. So that is the, so epsilon equal to delta by capital L. Then true strain is the sum of the all the strains over the original length. So here true strain epsilon equal to the summation of, so delta by L. So next we have to look for the stress strain diagram for the different materials, the two different brittle materials. So this diagram is very important for the competitive exam point of view. Generally they will be asked, so match the following questions. So this curve is suitable for which material? So here I have to look for the, this is for the brittle materials. We know the brittle material is not having the large deformation. So after, without any indication only it will be failed. So these are all the brittle materials. So for the high carbon steel and the cast iron and the concrete. So these are all the brittle materials, which mean large deformation is not possible. So without an indication only it will be failed. So here also see, there is a no deformation, large deformation is not there, and the material is failing, suddenly it is the failing. And this is the important points on the stress strain diagram, and thank you.